presentation?
Yes, we can.
Yep. All right. Take it away, Glenelg.
All right. Good afternoon. My name is Evan Lambert.
I'm Jaden Pithencolum.
And I'm Troy West.
And we're the Additive Manufacturing on the Moon team from Glenelg. With upcoming missions, NASA wants to send materials and goods to the moon, but they face the significant problem of the high transportation costs. And to potentially lower these costs, NASA wants to use materials on the moon and potentially additively manufacture on the moon with those materials.
Yeah, so just as it was mentioned in the problem statement, cost is the biggest problem NASA is facing with this project because sending materials from Earth to the moon is highly expensive. We researched that from 2006 to the first test launch in 2022, $49.9 billion were put into the Artemis program. And just to launch one of these rockets takes $4.2 billion. And with the materials that it would be carrying, an additional $1.2 million per kilogram will be used. And to lessen these costs, NASA will be using resources from the moon to benefit their needs. However, there is a problem on the moon, which is lunar dust, which is a fine powder that's about 20 micrometers in diameter that can corrode the suits of the astronauts. And since this dust is made from silicate minerals and has a high amount of silica, it can also cause silicosis, which is it makes it hard for the lungs to intake oxygen. So with our project, they can use stakes to strap down tarps to make less contact with the dust.
So to get an idea of what other people think of our problem, we conducted a market research. And one of the questions we asked involved the problem of cosmic dust on astronauts' boots. And in total, we got 106 responses. And all 106 survey takers felt that there should be some way of keeping dust off astronauts' boots. And another question we asked was about how significant they thought of the high transportation costs. And majority found that the high transportation costs could be a significant problem for NASA.
While researching designs for stakes, we came across some patents, and these are the ones that we liked. The first one on the left has like a removable tip on the end of it. We liked this design and thought we would try to implement it into our further designs. And the one on the right has a flat plate on the top, which would be good because we don't want the astronauts tripping on the stake that we make. These are stakes that are available on Earth today. The two of them are made out of plastic and one of them is metal. These stakes, while they do exist, we can't just send them to the moon because of the high transportation costs. The ground grabber stake on the left would cost around $200,000 to ship to the moon. The orange screw stake in the middle would cost around $60,000 to ship, and the metal one on the right would cost around $400,000 to ship.
So for our design specifications, we're constrained with the stake being 6 inches long. It should be lightweight, flush to the ground so that the astronauts don't trip over. It should include an attachment for easy drill usage, an attachment for guiding wires, and it should be able to strap down tarp.
These are sketches of some ideas that we had. The ones on the left implement like multiple parts and pieces, so you could possibly customize the stake or replace parts as they're broken. This would also make it easier to print without supports because you don't have overhanging edges.
Yeah, so to choose our best design for our final design selections, we rated each design on a weight scale with specifications including flush to the ground performance,
Can you guys hear
points,
me?
printability,
Yes.
aesthetics, simplicity.
I can't hear anybody else.
Hold on, team. Glenn has joined us. Glenn, we're glad you joined. I just told Stacy you weren't going to join. But you can't hear us. He has 2 frames going. Testing 1, 2, 3. Testing 1, 2, 3. You're doing a great job. I'm sorry to interrupt you.
It's all good.
Do you hear us now, Glenn? Yeah, he hears us. He hears us. Good. Keep
All
going.
right.
Yeah, so what I was saying was each design is rated based on a weighted scale based on the specification that's shown. And our top 5 designs will be CADed, modified, and tested in the future to help us choose our final solution.
So this is one of our mock-ups, and we just quickly designed a stake, regular stake. It has a height of 4.7 inches, a width of 0.5 inches, and the socket size is 1 inch. And some takeaways we got from this stake is that the threads were successfully printed. We didn't need any supports to print the threads. And we also found out that a socket size of 1 inch was too big and not suitable. So in future designs, we will make the socket size smaller.
This is the CAD design, and we actually 3D printed this design. It has some wide threads on the tip, and the tip and the shaft are printed separately, so we can avoid using support material. This is the 3D printed design that we have. The threads actually print without using support material, even though they look like they're overhanging a lot, which is good for us and means that we can keep on using this design for the future.
What is the orientation of the print?
It prints flat on the base.
Okay.
And so, yeah. And so the tip would be facing up.
Okay.
We tested these designs in dirt and in a hard gravel parking lot. The gravel parking lot is really hard and kind of tore up our tip, as you can see in the middle picture. But in dirt, it successfully went in on the left picture. For the shaft, we started testing different infill patterns, and that's what you can see on the right is a couple different infill patterns we've used. And we're still testing, but right now we think that gyroid infill is the one that we want to go with, or just increasing the density and the wall thickness.
And another thing we have to consider is the amount of dust that's actually we disrupt around the stake while we drill it. Because when we were testing this tip in the gravel, there was a lot of dust that came out from the gravel. And if this were to happen on the moon, then cosmic dust would go everywhere. So we'd have to find some ways to potentially lower the amount of dust that we spread out.
What speed how fast were you rotating?
I don't know. We're using an impact drill, and so in this video you can see us.
Okay.
Wow.
This one actually broke, and so that's our presentation. Do you have any questions? We can show you the shaft once we stop presenting.
Can you play that again?
Yeah, play the video again. It was too quick.
Wow. Okay.
Interesting.
Okay, and that's an impact driver, right?
Yeah.
Okay, that's actually kind of interesting. So does that, you're putting it in with a shaft, does that shaft disconnect and come out also? Is that right?
We're trying to figure out a way to make it lock in, because in the sketches you could see we want to have it assembled to where you can hook onto the top of the shaft and connect things to it. But for right now, we haven't figured out a way for it to actually lock in. So we're trying to figure that out.
Okay, very good. Could you guys do you have any of those with you right now?
Yeah, we do.
Oh, could you hold up each of them so that we can look at them a little bit more clearly.
Okay, so this
So-
is,
That's the tip.
Okay.
yeah,
For the connection.
and then the connection is right there. And then this is the shaft.
I see.
All right.
Yep.
So lock your shaft into it. Show us that.
And so it goes in, and then it would twist, and yeah.
Okay.
Very
So
good.
can it twist either way?
Yeah.
Yeah.
Okay.
Very good.
So
So
what is the size of the nut head on the top?
Right now it's 1/2 inch.
It's a 1/2 inch. All
Yeah.
right. So you drive it with a socket.
Yeah.
very good.
Okay. So the test material probably just needs to be raw concrete, right? Without adding water. It's just a concrete mix that you kind of let it pack a little bit, kind of take a bucket, fill it with this concrete mix, and then tap it so that it settles. And that really needs to be your test bed.
Okay.
And take videos of it too when you're doing that. That was good video. I
That
would
was
have
very
liked
good
it.
video.
I like it in slow motion if you can, because it
Yeah.
was so fast.
And I think it was the impact action that actually made the dust come up. If it was a rotation only versus an impact, I don't know that you would have got that dust come up.
And I don't know that I'd be too worried about the dust so much. Yes, it is something that we'll think about, but right now I'd like you to just worry about how well you can get it to stay in the ground.
Okay.
Mhm.
So now the first one you made, it was more like just a like a large bolt. Is that right?
Yeah.
Okay. Did you do any testing with that?
We tried to. Yeah, I don't know. We
We
tried
tried
to,
to,
and we ended up breaking it.
Yeah.
And so, yeah.
This is a look up right here.
Okay.
So you can see like it broke right where the threads start, and that's because that's like where the infill pattern starts. So,
Right. Okay. No, and I was just curious. I suspected that it would not do so well in the dirt, but I really didn't know. I was just curious what you had found. Now, on the other one that you had, hold up the other one. And then, so right now you've got it so that there's a pretty strong, the central core of it is a pretty sharp taper. Why'd you choose for the taper to go so wide at the top?
I don't know if I can really tell you, but I don't know. We just chose a cone shape just because it's an easy geometric shape that goes to a point.
And there may not be anything wrong with it at all. I'm just asking questions because it looks different than some of the other things. And my first thought is that when you have that big of a central shaft, that you're pushing a lot of dirt outward as it goes down into it. And I don't know if that, but there's also reasons why having it wide like that might keep it strong enough so that it's not, so that your threads are not separating from that central core. So continue experimenting with that. It looks like it's holding into the ground very well. I'm curious how it will do with the when you put it into the lunar regolith simulant. Excellent job, team.
Mhm.
What do you think your next steps
Mm-hmm. Lots of testing.
are? Okay.
We're gonna get some concrete that we can test in. We're going to start testing forces what forces they're braking at.
Okay.
How are you going to measure the forces?
Probably like a torque wrench. Right now, we would want to test what it's braking at when we're putting it into the ground, because that's the biggest problem right now. Is it's braking when we're drilling it into the ground. But then after that, we would use a force sensor to pull it out.
Okay.
Yeah, and you can once you get your regolith simulant, you can probably just use like some of the fish scales, like what you might use in your physics class. Does that make sense?
Yeah.
A luggage scale.
Oh, that's a good one.
Right. Because a luggage scale usually has a little plastic knob on it that will stop moving at its highest weight.
There you go.
So, yeah.
Excellent job, team.
Very,
I'm sorry
very
I came
good.
in late, but I think you guys are on the right track for a really good product. Keep it up.
Yeah,
Thank you.
I really like your design. Don't forget, you also have to do a stake at an angle with the loop for a cable. So there's a lot more to do, but you're right on track. Thank you so much. Do you have any questions? We got the experts here, so ask away if you have any questions.
Do you know what an expert is? It's a drip under pressure.
Oh my goodness. Well, Stacy and Glenn are real experts, so and they're not drips under pressure.
Okay.
Yeah.
But you can always ask questions. You guys know how to do that. So thank you so much. And I'll put this video online, hopefully this afternoon. Thank you.
Thank you.
Thank you.
Thank you.
Have a good afternoon there.
You too.
Thanks. All right, so we're gonna leave Maryland and go to Wyoming. Good morning, Scott.
Good morning.
Did you get snow? Did you get snow last night?
Oh yeah, we've been getting snow about every day.
Oh my goodness.
Wow.
Yeah. So it's not bad.
We haven't gotten any down here in Texas.
Darn.
Wait till I visit, you will. I'll bring the snow.
Okay.
Yeah, you don't want it down there.
Well, we still got a hurricane coming, so that's our next thing.
Oh no. That's not good.
Yeah, we'll see.
This weekend, we'll see. Yeah.
Yeah. Okay. Well, Scott has several teams that are going to are you going to do the additive manufacturing first, Scott?
No, I got my solar panel.
Okay, yeah. Solar panel first.
Deployer. Yeah. They're getting ready.
Okay.
And then we'll do the additive manufacturers.
Okay.
After
Good.
that.
Terrific.
Yeah.
Sounds good.
So where's David at? Okay. Take a sit, guys.
Come on up.
And you actually have something to take your side. Oh, I like you, but you don't know.
Oh, we have paper. Never mind, we don't have paper.
So here, this is yours. Solar panel. When you have to do your presentation. Okay. All right.
Awesome. So if you move the camera a little bit down, we won't see so much of the ceiling. And we get to see, yeah, that's perfect. You can see their sewing machines. So they have 2 classes now, one for design and prototyping and even a biomed, and then one for sewing. And that room with sewing is surrounded by 3D printers that the students use. And
Very
this,
good.
yeah, and this team is young men that have been in it last year.
Oh, very good.
Yes. All right.
This is our first year.
Oh, this is your first year
Yeah.
for both of you? It's the other team that's last year students. Yeah. Okay. Sorry about that. All right. So do you have a PowerPoint to share?
Do we need our books?
No.
No.
And introduce yourselves too.
Oh yeah. I'm Pauline Ferris and I'm a junior here.
I'm Roland Burton and I'm a junior as well.
Awesome. So
Very
you
good.
can join us next year too then.
Yeah. Boy, it might be all of them.
Is it all of them?
Oh.
Or should we just do the slide?
I see that.
No, the slide.
Yeah.
All right.
Yeah. And if you want, you can put it in a slideshow. You see that link that says slideshow at the top? Yeah, right there. See if that works. Yeah, that's perfect.
Our other partner, Avon, isn't here. I don't know.
Okay.
No way is that.
Yeah. We're gonna see if we could get a hold of him.
Okay, because if he's home, he can always.
Never mind. He's here.
Oh, he's here. Good.
Introduce yourself.
My name's Avon Posey.
Hi,
I'm a
Avon.
You want to start this after?
Yeah. Solar panel deployer, Marlene Ferris, Roland Burton, Avon Posey, Scott Christine, Wyoming Indian High School. I can school. Oh.
You can make it small.
Define the problem. The problem with the satellite is it needs a large amount of power from the array due to the satellite not self-orienting itself. So the solar panels are only expected to be collecting light 30% of the time.
All right, the criteria and constraints. In order to produce an effective design, the following constraints must be considered. Fit within 1U on the front of the 2U satellite. Provide maximum power available to satellite for the volume available. The more solar panels your team can deploy from the volume, the more power they should produce. Deploy within 2 minutes after being ejected from the deployer should not induce a rotation or vibration of the satellite panels. Can deploy in any direction. Only has to deploy, does not have to be able to retract. Solar cells can be rigid, more efficient, or flexible, less efficient. Solar panels can be expensive, so I don't expect you to demonstrate power, but your prototype should be mechanically accurate as possible, mimic wiring and panel thickness as it will affect deployment. 5. Deployment. The solar panel slowly is a virtue as it will minimize wobble or of the satellite. The more stable the satellite after deployment, the better the picture it will be able to take. The better the picture it will be able to take. It doesn't necessarily have to be symmetrically shaped once deployed, but make sure the deployment doesn't start the satellite spinning or wobbling because it was thrown off balance. Deployment doesn't have to start the satellite spinning or wobbling because it was thrown off balance. Along with the constraints listed above, the different environmental factors of the moon should be examined and implemented into the solar panel design.
our idea of solar panels are using the solar panel charging that usually takes like those three are our main solar panel ideas. With the first one having a pro of being foldable and is compactable and is 4 solar panels. And our second one also folds, but it is more wider than the first one. And our third solar panel idea is bendable, so it can be more flexible and be able to pick up UV light easier.
The pros of this product is that it's lightweight and it has high efficiency. The product has a good durability and it has 10 solar panels, which could help us make our own design to make it unfold. The con of this product is that it is only 50, I don't know what that stands for.
Millimeters.
Yeah, times 50 millimeters. Summary, the specific solar panel has good durability. It has 10 solar panels. It is lightweight and it is 50 times 50 millimeters. The pro of this product is that the box is made with a good quality and a durable plastic. The material of the product is BPA free. The con of this product is the lid of the box. Summary, this product uses a BPA free plastic that is also good quality. The length and width of the product are good for this prototype.
Brainstorm and ideas. Our main ideas for the solar panel is slowly extend out by using a fish line or metal extender to pull or push the solar panels out, absorb UV lighting.
That's it.
Yeah.
We have the box on us.
Yeah, so stop sharing so we can see the box. I'd like to see how you used a fish line to pull it out.
We haven't done the fish line yet.
We didn't get the fishing line yet.
Yeah.
Yeah,
Still
Okay.
waiting on it.
we just have the metal rod thingy.
Yeah.
Yeah,
So
show us that.
it's gonna have to be upside down, basically.
That's okay.
But this is what we want the red box to be. We didn't have enough tape, but we were gonna make more kind of just to mimic the solar panels, but we didn't have enough tape to put multiple cardboard on it.
Mhm.
Sure, that's okay.
That was supposed to.
And then that extracting things in there.
Yeah.
Yeah, the rod.
Yeah. So
Yeah.
when you take it out, it's supposed to expand outward with this thing. So like it will expand.
Oh, so it's like a drawer pull, like a
Yeah.
drawer thing. Okay,
Or
and
slide, yeah.
what are you guys going to use that for?
So the solar panels could
Slide out.
slide out of the box.
Yeah.
Oh, okay. Well, and I don't know if you'll need that because all you need to be able to do is for your solar panels to just be able to fall out of to be able to come out of the box as well. And so I don't know that you'll need the hinges or I mean the drawer pull for that. Does that make sense?
Yeah.
Okay.
What you would need is a latch on your door that you can open so that it can go out. Does that make sense?
Yeah, it just needs a latch or something
Yeah.
like that. Okay. Now, tell me about that bread box that you've got. That's also really interesting. What were you guys thinking about that with that?
So it was like the bread box was supposed to like when it's getting deployed up there, it was supposed to be see-through and supposed to protect the solar panels from the inside before it gets deployed.
Okay. Now,
But we also have to get around the lid
Yeah.
of the box somehow. Yeah.
well, and so if you look at the deployer pictures that we've got, there's 2 doors that open up, right? And so as those doors open up, there's a spring in the back of the deployer, and it's going to push the satellite out. So as soon as the pin moves for the doors, the satellite is going to get pushed out. Does that make sense?
Yeah.
So I don't think that there will be a lot of resistance from it. Now tell me about the solar panels that you are looking at.
So
Have you received them yet, or is that something that you've
no,
ordered?
we haven't.
Okay.
The two that we wanted to probably, could I share it? Or?
Yeah.
Yeah, sure. Yeah. Have these already been ordered?
Yeah.
Yeah.
Okay.
Yeah. Click on.
Oh. So the ones that we're prioritizing are this one because it can expand, you know.
It's
Go
portable
to the
too,
next
so
slide.
Yeah.
Oh,
And then we were also prioritizing this one as well because it has 10 solar panels
uh-huh.
and yeah.
We could like create our own.
Okay.
Yeah, we could like build it, I
yeah, we
guess.
can make like our own size of them. They don't have to
Okay.
be 50 by 50 or
And I like that one. That one's interesting. However, I think these are covered with epoxy, and that's not necessary for what we're doing because we're going to send it into space. We don't need something coating it for the
Which one's
protection.
covered?
The one on the left there that
Oh,
we're looking at, that one has an epoxy covering, I think.
okay.
And so if you guys did a search for small solar cells, you would get some solar cells that were not coated in epoxy. And what it would mean is that they would be a lot thinner and you'd be able to put more inside of your container. Does that make sense?
Yeah.
And they're also cheaper. So you can
Solar
get
cells?
100 of these for like about $16. So they're only like 16 cents a piece.
yeah.
So Glenn, the one that they ordered with the 10 solar cells that are 50 millimeters thick.
Mhm.
So that means 5 millimeters solar panel. And that
Well,
is thick, isn't
yeah,
it?
I don't know that does it
Yeah,
say that
that's
they're
not the
50?
thickness.
That's
50
not the
millimeters
thickness.
is
That's
not
how
the thickness.
they're
Oh,
rectangular.
okay.
So
They're
they're
probably, they look like they're about 3 millimeters thick.
Yeah.
Yeah,
And so the ones, I think you can get them without the epoxy, and they'll be like less than a millimeter, on the order of about a millimeter thick. And that means that you'd be able to fit in almost 100 of them within that area. But of course, there's going to be some hinging and things like that if you use that. So this is not a requirement, but it's something so that you'd be able to get more power out of the area that would fit inside this box. Okay.
Yeah.
Yeah, because the thinner the solar panel, the more you can fit into that 10 by 10 by 20 millimeter box. Does that make sense?
Yes.
Yeah.
Yeah, and we want as many as possible.
Okay. Now,
Okay.
and remember, you don't have to use. It's not even required that you use solar panels. But all I'm trying to suggest is that you can get some materials that are more realistic for for your demonstration. Another way that you could do this would just be, so like, business card, or I mean so like a credit card is a lot closer to the thickness of a solar panel than some of these other things. And so if you were to take a whole bunch of uh, like credit card kind of things and stack them all together, that would be pretty close to what we'd be doing as well. Does that make sense?
Yeah.
Yeah.
Now, how do you want to stack them in here? How do you want to stack them up? And how do you want them to spread out as they come out? Have you guys thought about that?
We just want to hold the bread box upside down
Okay.
and then just hope it like can contract.
Well, we need
So
something
how
like
are you going to put all of these together? Are they going to be taped together so that they fall out and kind of like this kind of thing? Or what are you guys thinking?
Most likely, yeah.
So there's a lot of different ways that they can come out. In some, it'd be one thing for them to come out straight, and that's perfectly fine. Do you want to have, if you have solar panels all pointing in the same direction, that gives you one thing. But then if you do you want to have solar panels back to back so that they can gather sun on depending on what direction they're pointing? Do you see what I mean?
Yes.
So there's other options there as well. And it doesn't just have to be one way that they come out. It's possible that you might have, so are your solar panels going to be the box, or are they just coming out of a box?
Coming out of the box.
Okay. And so if they're coming out of the box, can you put solar panels on the outside?
Yeah.
Yeah.
Because that's another place where you can gather solar energy from. Does that make sense?
Yeah.
Yeah.
And there's not a requirement that there has to be a box, because the solar panels can be the box, and then they can also expand from that location. Is that okay?
Yeah.
Okay.
All right.
Excellent job, guys. Any
Stacy,
thoughts or questions? Oh, go ahead.
Stacy, you have any comments?
So I just want to kind of throw out some ideas I think that might be a little bit clarifying. So if so, like what Glenn was saying, if you had it on one side as it came out, then basically you're just talking about a single plane, right? If it came out, and it might unfold to create that plane. If you had it on both sides, right, it still can fold out in kind of a plane, right? Now, the other thing is what if it came out like a telescoping spy scope, right? But now it's a box, and it comes out so that you actually have solar panels on all four sides. Are you tracking with me?
Yeah.
Right. And so what does that mean if you would have actually solar panels on all four sides? It
would be on like the outside of the box.
Right. It would be like on the outside of the box, but you would have a box within a box within a box within a box, and the thing would just kind of telescope out.
Yeah.
Right. But then how will where the sun is relative to your system, your solar system would then be able to collect power more than 30% of the time, right? So if you only have one side of solar cells and you don't have a way to orient the little satellite, and we're saying that, okay, 30% of the time you'll be able to generate power, right? But now if you put solar cells on both sides, have you doubled that 30%, right? So if it was a triangular shaped thing, you would, right? Or if it's on four-sided thing, then you've increased your ability to produce power most of the time throughout the day. So think about that as well a little bit. Okay.
That's a very interesting idea. You'd have to use smaller and smaller and smaller panels, yeah, solar panels.
Right.
But you don't necessarily have to keep it as your square. You could make it as a cylinder or some other shape that maybe would even collect more energy.
Right.
A smaller and smaller cylinder as it comes out. There's
correct.
That's the creative part that we want you to think about in this project. How to get the most the best design to get the most volume exposed to the sun. Does that make sense?
Yeah.
Yeah. So think creatively, think outside this box. Do you have any questions for us?
No, I think we're good.
Okay. And you can contact me anytime and we'll have another Zoom soon. How's that?
Yeah,
Yeah,
that's good.
Okay, thank you so much. Glenn,
Thank
did
you.
you
Good
have
job.
anything? Good job.
Very
Thank
good
you.
job.
I like what you're doing. Keep
Yeah.
this up.
Yeah, keep it up. Absolutely. All right.
Awesome.
I've got to go.
Okay,
Y'all have fun.
Stacy. Thank
Okay.
you. All right.
Bye.
All right. Bring on the next Wyoming team. Good job, guys.
Like that.
This is good, Flo. How many teams do we have today?
Not that many.
Okay.
We got 3 Wyoming teams. We just did one. And then we have some Laurel teams. And I see Devin has the teacher is not there, but Devin has taken their place there. And that's in Laurel, Montana. And then the last one is Jackson Hole. Hi, Scott.
Hello.
So now we're doing additive manufacturing, right?
Right.
Excellent.
So yours is up on the top.
Good morning.
Good morning.
So they have 2 additive manufacturing teams.
Are you using this? No, we're using this. You gotta have. Oh, wait, you already have it? I think so.
Yeah, so you can share your screen, but introduce yourselves first.
My name is Martin Underwood.
My name's Laurel.
We are currently down a member. Rest in peace. Just no, that's he went to Hawaii for the week, so he won't be here.
That's okay. You can carry it on, right?
I would like to go to Hawaii for the week also.
I think he's at least. Sure. So that's Zion. Just go back. Go out. And then click out.
There's no wrong.
Oh, that's
Here
there we
it
go.
is.
Good.
Hold up. Yeah, sure.
Let's go back there.
You open this all the way. You okay. There it is.
Yep,
Okay.
we're getting it. Yes. Perfect.
Stakes in space. Because it's the okay, go ahead. Stakes in space, additive manufacturing, Scott Screen, teacher, Martin Underwood, Noah Redbilla, and Marley's here. He's not here.
Okay.
Yeah. Definition of the problem. When astronauts are outside of their lander. They have a large amount of lunar dust attached to their suits. They are thinking of using a tarp outside of the lander to get as much of the dust off as possible. In order for the astronaut to not slip on the tarp, it needs to be held securely with stakes. The lunar stake should also have other functions, and it should work with the suits and bulky gloves. Criteria and constraints. Cannot have sharp edges, maximum length 6 inches, must not be a trip hazard, must include an attachment to a drill, can be driven into the regolith using a drill while in a spacesuit, which allows crouching but does not allow kneeling. Okay. Your turn.
We research different types of stakes to use for our design. Then we research the surface of the moon. Oh, what did I do? Brainstorming ideas. The stake will have a special triangle top, as is the strongest shape in nature, in Marley's words. The stake will have a bore which will be drilled into the ground. This stake doesn't include the attachment place for guide wires, and we can't have a pointed tip. This shows the drill bit that we designed. Yeah, we picked the triangle shape for the bit. Stake is like screw. This design has flaps on the side for the stake. The flap's purpose is when you put the stake in the ground, the flaps will add resistance when you try to pull the stake out. These are our prototypes right here. The stake, the red stake is the first prototype, which doesn't have. Well, we'll get into that, but that first one doesn't have the triangle drill bit yet. This is a little table we came up for the stakes. We have all the data for them in there. We haven't been able to test them yet, but we will start next week.
That sounds good. Are you guys going to so are you printing a an attachment for your drill so that that'll fit into that triangular piece?
Yeah, we would show you, but our friend, he took off with his Chromebook, so we can't get into his thing right now. So
That's fine. And so have you guys taken these outside into the sand or anything like that yet?
Just one of them we tried in the dirt, but it was
Sure. Oh, okay. Hold that up close. Do you have more slides?
Yeah, we have more slides. Yeah.
Okay, let's go through the slides and then I'll have you show me all that stuff better.
Yeah. The pros of prototype 1, it has a hook for the guide wire and is big enough for the astronaut gloves to handle easily. But the cons are it will be a trip hazard as it is rather large and it has no attachment for the drill. And the spiral adds a lot of support material and has a sharp tip.
Okay.
Prototype 2, the stake will not be a trip hazard and has an attachment for the drill. But the cons are the stake has a pointed end that will be sharp. The stake is just a pole with no spiral or anything like that because of a printing error.
Okay.
The pros of prototype 3, not a tripping hazard, has an attachment for a drill and has spirals that only go halfway up for less support material. But the cons are there's no place for the guide wires and the spiral is too small to be effective. Wait, is it? Oh.
Okay.
That's it. Yeah, that's it.
Okay, stop sharing so we can actually see that.
Yeah, let's see what you got.
Here's a prototype 1.
Okay. And I like that. Now tell me about the central shaft is pretty large, and then you've got some pretty good sized threads on there. Why do you think you need such a large central shaft?
Because of the astronauts' big old gloves.
And so it wouldn't snap easily.
Okay. Now, and with plastic, I think that's accurate. But you can imagine if you had a thinner piece that was made out of metal, it probably wouldn't be too worried about it snapping, would you?
No.
Okay. And show us the next one. You said you had a printing error with that one?
Yeah, this one. It's just a pole.
Okay. Yeah, right now it's just a stick.
Here's that triangle.
But I like that idea as well. I think that was pretty smart. Okay. And then you had a third one?
Yeah, here's the third one.
And that one looks a lot better.
Yeah, this one. It only goes halfway up, so it doesn't have supports all the way. But these are too small. You're making bigger. Next print.
Okay. Now, what direction did you print that? Was it laying down or was it standing up? What were you thinking?
Laying down.
Laying down. Okay. And there were no supports for that, or there were some?
There were.
Okay.
They're
So we're looking for ways to minimize the amount of support. So, for example, if you print it this way, right? Could it be printed going in that direction?
Probably not. That support's going all the way up.
Well, and so you have to look at that and see if you can make it so you don't have supports. And the ways that you might do that is that if you have a 45-degree angle, it won't have to print supports. 45-degree angle or more, right?
Yeah.
If your spirals that are going up have a little bit of an angle to them, then they may not need the support material. The other thing is, instead of printing this way, you might print it that way. Okay. And then as your spirals go up, you would have like a slope in this direction, but you wouldn't have to have a slope on top. And so as you try to pull it out, it would hold on to more dirt. Does that make sense?
Yeah.
So take a look at different printing methods, and it might improve your spirals as well in terms of how much you have to support material you have to pull off. Okay.
Mhm.
I think it's looking really good, guys. What do you think your next step is? What do you want to try?
We're thinking of experimenting with the infills of the stake.
Okay.
Get less weight. With
Okay.
more.
How much infill does that have? Do you know?
I think this one's 60%.
60%? Okay.
Yeah.
Now, what kind of shapes do you get for those infills? Are they rectangular, triangular?
Oh, we don't know yet, but we're gonna use the good machine next, and we're gonna choose the infill shapes.
Okay. And you can choose that in there. So I think that's a great idea. So look exactly how to choose that. I'm not sure. I think it's probably under the advanced settings. But that's something that I think is really valuable. My first guess is you probably don't need more than about 40% infill. That's just a guess. Okay.
Right.
Excellent job, team. Keep this up. What software are you working with?
SolidWorks.
SolidWorks? Okay. Very good. And I think that that'll help out a lot as well. They can give you SolidWorks. If I believe you can choose some of the different. Let's see, the infill I believe is all in the software for the printer. But I think that the way you position your threads for it, that's all going to be in your SolidWorks, and they can give you some suggestions there too. Okay.
Mhm.
Good
Yeah.
thoughts. Any other thoughts for him, Flo?
So, yeah, I like your suggestion on trying to make your swivel things around it at an angle so you don't have to have scaffolding. But when you do, I need you to not only take pictures before you scaffold your part right off of the machine, take a picture, then weigh it. So we need the weight with the scaffolding, and then take another picture after you scrape off the scaffolding. Weigh your scaffolding too, and also take another picture and weigh the part without the scaffolding on it. But try, as Glenn suggested, different angles to put that stuff around it. I don't know, the threads, I guess you would call it, around it. What do you call? What do you
That's
call
the
that?
support material.
Yeah.
Support
she
material.
means the threads. Yeah.
To use the
frame
least
the
amount of support material on that. Okay. I'm glad you're all doing 3D printing, and you have three things to worry about besides your scaffolding and your infill: the size of the threads and the size of the main stem.
The main
That-
shaft. Yeah.
Yeah, that would all be important to come up with the best design, strong enough but light enough that it doesn't use up any of that precious aluminum that's on the moon. Do you have any questions for us?
Hey guys, can I ask a favor? Can
Sure.
you show me the head of your stake again? You have like a triangular indentation, is that right?
Yep.
And are you printing a triangular head that goes into that?
Yeah.
Is that how it's going to be attached?
Yeah.
Oh, okay. Very good. So I was just at a school this morning talking to some other students about this project. One of the things that really is not part of the design requirements, we didn't put this into the write-up, is the ability for your stake, to attach to some kind of an adapter that the astronaut can then take and, use a drill to work into the soil. But obviously, one of the things that needs to be taken into account is that when you put these two together and you turn this downward, that the stake just doesn't fall off the end of the drill bit, right? And your smiles might indicate that it's already happened, right? Nevertheless, just make sure that you add enough friction, right? So that as your piece is going into the head of the stake, it's going to hold enough for somebody to now be able to turn this vertically and put it down, because obviously we want you to use a drill bit with some kind of an extension on that. I've suggested to teams the simplest thing is to just go get like a 1/4 inch diameter piece of doweling, and you can make that any length you want. And then you can put your special adapter, you can glue it or tape it to the end of that dowel so that you can drill with, right? But the whole point is you got somebody in a pressurized suit that has to kind of attach that stake to this drill bit and then turn it and go down. It can't fall off of there. The other suggestion I'd have is you can always try reducing the diameter of that tarp stake. I know that you have it a certain size because you want it to have enough strength to withstand force when it's pulling out and not break. But there's no magic number there, right? We don't know whether the stake needs to be 1 inch in diameter or will a 1/2 inch in diameter. And I'm talking basically the central core, right? So that's something that I would play around with. Try to make a smaller diameter one, and see how effective it is. It's kind of hitting that Goldilocks zone of just big enough to make it strong and not break, but not too big. Because again, if you oversize this, you're just using a lot more material unnecessarily. And make sure that you document all of that in your testing. Your testing data is going to be really important in determining, the finalists.
And don't throw away the 3 things you just showed us. That's important information too, that we want to see how it progressed over time. And thank you, Dave, for that.
Yeah.
That really was helpful too.
Good
All
comment.
right. Yeah. Any questions, guys?
I don't think so.
All right. You can always send me questions.
Okay.
So
Good
thank
job,
you
guys.
so
Keep
much.
this
Yep.
up.
Good job. All right. So we have another additive manufacturing team there. Bring on the ladies, I believe.
Terrific.
When you go to share, yours is up there too. You can just click on it and share. Yeah, just tell me your other two isn't there. Oh.
Then after this team, we're gonna switch to Laurel, Montana. They also have a stake team.
Just go and do yourself first, and then I'll have you share.
You want the camera or my?
Good morning.
in your group. You're here for moral support.
Hey, ladies, how are you doing? It's good to see you.
Hi.
Hi.
Sorry. Good to see you. I'm Alicia. This is Natasha. She's not in my group, but she is taking notes for me.
Terrific.
Currently I am the only person in my group that's here, but I think the two other people will be here later on. But for now, it's just me.
That's
So
okay.
let's get started.
Yes. You can, do you have a PowerPoint?
Yes.
Okay. And thank you for taking notes, Natasha.
Yeah.
But I am recording this, so you will be able to see the recording too.
Additive manufacturing on the moon, 3D printing with aluminum. We are 3D designing a start for a stake for astronauts to anchor tarps or guide wires that astronauts will need to be able to do in pressurized spacesuits. We are to implement additive manufacturing techniques to design a good, strong stake that we used in lunar regolith. We know the parameters of the stake must not be longer than 6 inches, must not be a tripping hazard, must have an attachment to a drill or a handheld drilling device, must be attachable for guide wires or tarp materials, must be made out of aluminum, must hold in place effectively, must have a hole fit enough for a grommet, and is usable with large gloves, such as the ones on the spacesuits. And it must be inserted and held in various ground conditions at multiple angles and sorry, my nose is running. At multiple angles and what's the word? Material, concrete material, I think.
Just the powder, not this, not with the cement, just the powdered cement. No, don't add water.
And last but not least, it should be used with the least amount of supports, scaffolding, and material used. So keeping all this in mind, we did make a lot of different stake designs.
Excellent.
But for research, we reviewed different stake designs and we decided which ones would probably hold better. And we modeled some prototypes after stakes design. Like the one with orange, we made a model with similar design to that, and a metal one like this, and a few others that we made. We are using a mixture of groves, teeth, and what's the word? The reds. I think I'm using that correctly.
Threads, yeah.
Yep. Threaded designs for multiple stakes. We do have a few on hand and a few on file for computers, but for now we just have one. I'll show you that in a second. After we printed out some prototypes, we did weigh our material with and without the scaffolding, and it is roughly, there is a specific number, I can't remember it right now, but We did weigh them with and without scaffolding as per the instructions. And we do more research after we tested them, just for any problems or things that don't work while in use. But to remember things, we already talked about that. And we have also been researching types of infill to see which design pattern will intake the least amount of material and filament, and to see if it will be strong enough to be used for the stakes, such as the least amount used but strong enough to be strong, I guess. I don't think we have yet to make any stakes with the infill, but we do have patterns, such as grids, lines, triangles, trihexagons, cubic subdivision, and zigzags and crosses.
Okay.
There is a lot to test out, but we are only selecting a few of them to still keep time to make more stakes to test.
Okay. So you said that you've printed a few?
Yes.
Okay. Are those, is that all the slides you've got?
There's still more. Hang on.
Oh, okay.
Let's see. Oh, and we are trying to figure out
Oh,
a design
look at that.
for a guide anchor, such as these.
Yeah. Tell me about that. What's the one on the upper left?
Upper left. Mm, the upper left. The big metal one.
Yeah, I've never seen one like that. I've seen the others before, but I haven't seen that one.
I didn't put the picture up there, but we did discuss it. From what I could tell, when that particular guide anchor is getting screwed into the ground, it flays out underground.
Uh-huh.
Like, so it's drilled in like upright or compressed, and then once it's under the ground, it smooths out.
Spreads out some.
Yes.
Very interesting. Okay. Keep going.
All right. And we have been researching guide wires and seeing what characteristics is needed to like try and make a mock-up prototype in order for it to work, such as this swivel that will connect the guide wires. Like, make sure it doesn't get in the way of the drill or whoever's drilling it.
Sure.
Lots and lots of designs we need to be aware of.
Good job.
And we did draw up some designs that we showed last time. Mostly about how or what kinds of type of ways to insert the drills and stakes into the ground, such as handheld or hand drills, drill bits, and different handled attachments, I'm pretty sure.
Okay.
Like these ones and these ones. And we also have been researching different design types to see if it will be easy to make, such as these and that. And we have also been drawing up some guide anchors just to mess around with it a bit. The next slide. The anchor rod for research, we have been researching an anchor rod that needs to go into the opposite direction to create a counteracting force. This helps to stabilize the structure by balancing the force and preventing it from moving or tripping over. The data suggests that this method ensures a secure and stable anchoring system. Anchor rods are often installed at an angle to increase its resistance to pull-out forces. Its resistance against pull-out forces by creating a stronger surface area of contact with the concrete, ground, or dirt.
Okay.
And we have been trying to implement this in our design choices. And I think we tested it, did we?
You're going to next week.
And we are going to test it in a week.
Okay, that sounds good.
You're mistaken. This is one Nicole told you to try.
Yeah. And these are a couple of prototype stake designs.
Okay.
For threads, to see which ones would dig into the ground more efficiently and see.
Which ones do you think would work the best?
Last time Nicole was here, I did show her these designs, and we both like the one on the second to last on the right.
Okay, and why do you like that?
It has a thin amount of material, but it is also smooth enough to drill or carve into the dirt.
Okay.
The designs, because it's nice and thin. It goes along or slides along material that it digs into.
And that was astronaut Nicole Mann was there visiting them.
Oh, is that right?
Yeah.
Okay.
And she showed that to them, right?
Oh, okay.
And we did use the 1, 2, 3, 4. Yeah, the fourth design to make our first prototype, which was this.
Oh, okay, very good. And I like that. Okay. Have you printed that one already?
Yes, we printed out two. I think with both infills the same. We haven't been able to test it yet, but we do have some pros and cons.
Okay.
A pro is there is a a hole design for custom-made drill bits and custom-made hole attachments that are easily interchangeable. But a con is that it might be too thick to drill into the concrete powder with.
Okay.
So we might be looking to slim it down a bit.
Where would you slim it down?
Probably the OD outside diameter.
Okay. So do you mean the shaft itself, or do you mean the threads?
The shaft.
Okay, very good.
And we might decrease the amount of rotational threads.
Okay.
So right now there is 1, 2, 3 rotations.
Uh-huh.
But in the future we might do more or less depending on the resistance it gives us.
Very good.
I think that's a good idea. Yeah.
But for now, we just have one prototype printed out. Yes.
Excellent job, ladies.
Okay.
Oh, and it's heart-shaped.
Of course.
I think that's great.
In pink.
So can you stop sharing and show us that steak
Yeah.
a little bit
Yeah,
closer?
yeah.
I'd like to see it in more detail. It's pretty cool.
Let's see.
Well, that's
Show your hunch.
all right. What is the diameter of that central shaft?
Should be. You have it on the table?
Awesome.
Showing your table yet?
Not yet.
Okay. Tell them you have a table that has all that.
We do have a table that shows all the data and stuff for it. I'm just
Okay.
gonna pull it up real quick. See,
Mhm,
our
we see it.
steak at an infill of 40%, we have a outer diameter of 0.53 inches, a mass of 28.4 grams in mass with the supports, and a mass of 14 grams without the supports added. But
Wow.
So
That
half
was-
your mass was support
supports.
material.
Yeah. Now, see what happens if you were how did you print that one? Did you print it like this or like this or like this?
we printed it in. We printed it upright like this, so
Okay.
it did have a effect on the amount of scaffolding.
Okay.
But in the future, we are hoping to print it like this, so it doesn't gather up at the bottom like this.
Sure.
Mhm.
And I think that would work out. That might help you out some. Hold that up again for us. And so, the threads, let's see, by printing it tip down, you might have to build like a raft on the bottom so that it's a little bit more stable when you're printing it. Okay.
Yes.
But if your threads are up at an angle like this, it'll give you it'll make it so that it doesn't require quite as much support material, and that might help out. Okay.
Mhm.
That's a good
Excellent job. I like what you're doing with this.
So, ladies, let me ask you, the head of your steak, you're going to have a custom design heart-shaped bit that goes into the top of this so you can drill it in, right?
Yes.
Okay, that works. Now, my question is, talk about how you're going to connect this either to a tarp, or if you were going to use this to attach to a guide wire. How are they going to connect to your stake?
Let's see. We have been looking at some stakes with designs like that, and so far a few ideas have been adding a little loop or a ring, I should say, off to the
Okay.
side that could hold any lines or wires or we
Okay.
could even have some attachments to hold tarps. So like
Okay.
an interchangeable clasp.
So
But
are you thinking that if we're printing a whole bunch of these on the moon, right? And you're going to make a lot. So there's going to be an assembly time. Would this ring or loop be something that the astronauts would attach to all of these stakes before they take them out and try to secure them into the ground?
We are hoping to actually make the stakes that to be like all in one kind of.
Okay. All right. Very good.
But going more into the design aspect of it, it is having like a ring like this. Like on the side.
Yeah. Okay.
But
but again, don't you, if you had that ring attached to the side of your stake, that's going to add a lot more complexity to the print. And especially when you think that this is kind of extending out from the side, that would then probably require a lot of support. So my point is, do you have to print it as one piece? Could you not print this as the stake and then your attachment? And again, before you go and start doing work outside, and you're still in a shirt sleeve environment, you could connect these rings to each of those stakes and then just take them out and drill them in. Does that make sense?
Yes.
There's nothing that says you can't do that. That it would be a totally acceptable way to do it, and it might simplify the print itself. So a little food for thought. You guys go with whichever design you want, but again, try to keep it as simple as you can.
I have actually not thought of that, but thank you for bringing that up to me.
Yeah.
We will try and incorporate some of what you said into our next few designs.
Good. Okay.
Yeah, that does open up a few solutions to us. But thank you for pointing it out.
By the way, can I ask real quick, have you already got some dry cement to test with?
Yes, we do. I think we have
Okay.
4 gallons of it.
Okay, so and I'm just wondering, is it just like cement mortar, or is it like Quickcrete that already has a lot of rocks in it?
Quickcrete. It says Quickcrete. So
yeah,
it has the
and
rocks.
that that's material. Normally if you're pouring concrete, you add the rock in amounts that are based upon what kind of structure you're pouring, what kind of forces it has to adapt to. That Quickcrete, and I'm saying this because I was in a school this morning that had a bucket of this Quickcrete. There are a lot of rocks in there, right? It's like a whole lot of pebbles, and probably more than you should be using, right? I would recommend getting a bag of just, concrete, just the powder without any rock in it at all. You can then add as much or little additional rock as you want, but it would be kind of nice to test this in just the concrete itself without any rock added.
Yeah, so it's more like a mortar, like what you would put between bricks. I think Dave's probably right on that. I think you want to start with a mortar and then add some gravel to it as you go.
Yeah. Oh, I definitely the Quickcrete I saw this morning. It's just got so
it's
much
lots of
cobble
rock
in it that it's just it's not going to hold anything.
I think you're right.
Until you add some water to it.
And then it'll hold.
Okay. Nice design, ladies. I like what you got there.
Awesome. So I I love your 3D printing, and also your table is perfect. That's the information I saw. You haven't put in all the, all the columns, but that information is really what we're looking for. So keep that up. We appreciate it. And you can always ask questions. Do you have any questions now for us?
Not currently, no.
Okay, make sure the other two ladies get to listen to this presentation. I'll put it online. I'll send Scott the link. But nicely done. Thank you so much. You guys, you gals have a great afternoon there.
You too.
Okay.
I'll probably email you if we do have questions later.
You bet.
All right.
Anytime. Thank you. Have a good afternoon. Bye-bye.
Thank you.
Yep. Bye-bye. All right, Scott, we're going to go on to Laurel.
Okay.
Thank you so much.
You bet.
The kids are doing well.
Yep. Okay.
Okay.
See you later.
Bye-bye. Yep.
Bye.
Bye-bye. Bye-bye. All right, Devin. Do you
Thanks again, Scott.
Yep.
Yeah, thank you.
Can you guys hear us okay?
Devin, thank you so much for joining us today. I know Mr. Hill wrote me an email. I was so sorry to hear that he was in the hospital.
Can you guys hear us okay?
Can you guys hear us?
We do. We hear you, and I see myself on your big screen in the class, in the front of the classroom.
He's working to fix it right now.
Oh, yeah, I see Devin. So has Devin been your substitute teacher, or who's been your substitute teacher?
It's kind of been changing for the past week or so. But yeah, today Devin's our substitute.
Good. And I'll try to come and visit you as much as I can. This week I'm got PDRs all the time.
So yeah. Right now, we got the stake project. That's what we're going to be presenting today.
Yes.
We haven't done much work on the lunar landing legs yet. Like we told you when you came last time, we're planning on doing that later after we had completed the stake. So, yeah.
You bet. So this team has chosen to do 2 projects, but they're going to concentrate on the lunar leg project first and then go on to another one. So, and introduce yourselves. Do you have a PowerPoint?
We do. I believe Mr. Rodabaugh is putting it up now. My name is Zach Wonger.
My name is Jacob Novak.
This is what we like to call LASH. Stands for Lunar Additive. Oh, sorry. Lunar It was Lunar
Additive manufacturing.
Yeah.
Okay. Do you have some of your prototypes right there? You want to show those to us first?
So this is that we chose to do. This is kind of our final design. We do have to change some parts about it. Firstly, we don't like how the threads, instead of coming out like you've seen on other stakes, instead they go in. We wanted to change that because when we tested the stake in concrete, it didn't really work very well. It didn't stick in the concrete. So we're going to change that hopefully in the future.
Now, so tell me, why do you have such a large handle on it? Is this just going to be put in by hand? Is this something that can...
Sorry, I didn't mean to interrupt you.
No, go ahead.
We chose such a large handle for the comfortability of the astronauts, for one, and two, to allow you to get a better grip if you are driving it into the ground by hand. Because with our other design that you can see on the screen there, the handle was too thin, and we were also worried that it might break if too much stress was put on that connecting point right between the handle and the actual shaft. And also those like finger indents right there, they were too small when we made them, so they didn't appear on the 3D print when it actually came out.
Okay.
So that's why we changed it to this. And we actually have this as a hex driver. So like a drill with a hex bit in it can drill this into the ground.
Okay.
Yeah.
So are those two different options, or are they both the same option where you put the handle on, or what are you guys thinking?
Can you repeat the question?
Sure. So you said that you've got it so it can be put in with a drill with a hex. Is that something where you add the handle to it, or are they two different options?
No, the handle and all that prints all at once.
Okay.
It's for redundancy, Glenn. In case the astronaut doesn't have a drill to do it, they got a handle to do it. Which
okay. I like the idea. I'm not sure that they'll be able to get to the ground to be able to put it in.
What do you mean by that?
Well, because of the spacesuits, they're not going to be able to get to the ground very well. They're going to be able to stand up, and they'll be able to kind of crouch down, but they may not be able to get all the way down where their hand could touch the ground.
Okay.
And they're not going to be able to do that repeatedly.
Right.
Even if they could get down there once, that's a lot of work.
So what they're suggesting is maybe we don't need that handle for redundancy because the astronaut wouldn't be able to kneel down close enough to the ground to actually use that handle. Does that make sense? I love that you have redundancy there, but when we start thinking about the spacesuit and the astronaut getting down to the ground to actually screw that in, it's not going to happen, it sounds like.
Another reason why we actually had the handle wasn't just for screwing it in, but that was one of the main ways that we were hoping to put the guide wire around the stake as it goes into the ground, so it has like something to hold it as you drilled it in, and so it like pinned the guide wire to the ground.
That's a good feature. Good job, Zach.
Yeah, and I think you can probably accomplish that without having it extend out so far.
Mm-hmm.
Yeah,
right? I think you can do the same thing. Just don't make those like a handle. Just some extensions that are enough for a guide wire to be able to loop around.
Yeah. So that's kind of that's our stake, I guess.
What do you have any other? Have you tried this in dirt yet?
We tried it. We have tried it in concrete. And so that's why we're saying we need to change the. If you can see on the screen, the threads, that's why we're wanting to change them out, because it's not holding inside of the concrete like at all. It was super easy to take out.
Sure.
So we want more material on the outside to like compact sort of the concrete. That way it adds like a substance to be screwed into, kind of.
Sure. Now, how did you print this? It looked like you might have printed it laying down.
Yes. Yeah. So you want to explain that?
Yeah. So the reason we chose to print it like this is so the layer lines are horizontal, which is going to add some strength to it.
I think that's very smart. Did you have any support material?
No.
Okay. And go ahead and stop sharing so we can see that a little bit closer then. Okay. Now go. And it looks like, do you have a flat spot on the bottom?
Mm-hmm.
Okay. And so that explains why there's no need for support material. I think that's very smart. but now we need to get it to hold into the ground more, right? And so, do you think you're going to have difficulties as you switch to having a thicker thread?
Yeah, we might need to add some more support if we go to like having it outside instead of how it is right now.
Well, and part of what I'm thinking about is that, the way you've got it printed is perfectly fine for us, right? If you're not having any support material, it's real quick for that astronaut to pick it up and then start using it real soon. So that works good for me. And I like that you're printing flat, because now you've got the grain following the whole shaft. And so that's also very smart. What kind of infill do you have for that?
We decided to do 100% because on our first print, we didn't do, I think we did about 65% infill, and it was kind of flimsy. So we decided to go.
And so the flimsiness might also be partly to do with the flat side that you've got. Just because if you've got a rounded shaft all the way, it makes it a lot stronger, just because of the dimensions that you've used for it. So I think you guys have some great ideas there, by going to see if you can look for ways to not use quite as much infill, because that'll make a big difference. Now, that doesn't mean you can't use it at all. It just means that you want it to be as lightweight as possible, so that you don't have too much, so you're not using more aluminum than necessary. Okay? Excellent job, team. So where do you want to go next here? What do you think your big changes are?
So the biggest changes, like we've discussed in this, is we're going to cut off the handles just about where the where your fingers would go. That way, it still has where the guide wire can go and hold on to. And we could actually add grooves around like the top part. So here, if we added grooves here, that way the guide wire has somewhere to fit into.
That's a good idea.
Okay.
Also, taking these threads and extruding them outwards instead of having them go in. That way, it works better when it's inside of concrete.
Sounds good.
Yeah. I don't know if you can see it, but right
here, I see. Now I can see the hex. I didn't understand that before. That's very smart, guys.
Yeah. That's where.
Now, did that use support material in there? Did you have to pull that out?
It did not.
That's excellent. That's terrific.
Yeah. Also, the actual shaft is tapered downwards. It's very slight, but it's kind of like a triangle shape almost.
Yeah.
And Devin kind of helped us with that. He would give us that idea, because he said that it makes putting it into something that's soft, like the concrete or like the moon dirt. It makes it the displacement of the dirt makes it compact and makes it a tighter fit when it's inside.
Yeah. No, I think you're right. Okay. So is that shaft? So are you going to lay down the tarp and then put it through the hole of the tarp and then twist it down through that? Is that correct?
Yes.
Okay. Very good. How much of a toe jam is it going to be? Am I going to trip on that thing?
Oh, no, it lays pretty much flat on the concrete.
You think so? Okay. So keep that in mind as you're going, because that's also one of the components that we're worried about. Okay.
You would have
Excellent job, team.
With our design, you would have to like specifically be looking to trip on it to actually trip on it. You would have to like.
How much do you think it's going to stick up?
You can answer. The only part that's going to stick up is this like top handle part.
Well, the handle itself looks kind of big to trip on. So part of it's that distance up, and so decide how much of that distance needs to be sticking up, so that you've got less to trip on. I don't know about you guys. I can be clumsy sometimes and trip on a magazine or something like that. So just be aware of what you're working with. Okay.
Yeah. Just decrease the height of that handle to make it as small as possible. Does that make sense? Because you don't need it as a handle now. You just needed to hold that guide wire, which is a great idea.
So
Dave,
since we're
do you have, Zach, were you saying something?
Yes, since we're cutting off the handle, I think while we're doing that, we can also maybe cut the whole length in half to make it much less.
That's probably right.
Yeah.
Experiment with that and see what works for you. Okay. Good job, guys.
Thank you.
Nice job.
Awesome. All right. Did you have any questions, Jacob or Zach, for us?
No, not really, unless he does. No, I don't have any right now.
Well, you can always email me and I will try to come and visit you next week. I need to know your schedule when you are in class. So I'll ask Devin to send me that schedule for next week. Okay, thank you guys. So the next team, have a good afternoon there. The next team is also from Laurel, and they are actually doing the cosmic dust collection.
Good.
There's two teams that are doing that.
Okay, ready? I guess which team wants to go first? Either or, pick now.
Good morning.
Good morning.
Hi, team. How are you doing?
Pretty good. About yourself?
Excellent. Okay.
Wow, Devin's on top of it. Thank you, Devin, so much.
That was supposed to say both our names.
Yeah, I see that.
Well, I'm Shelby Munson. That's Marshall.
Okay.
Hey, Shelby.
Okay. So we're doing the cosmic dust collecting. So the problem we're trying to solve is we need to be able to collect the dust off of the outside of the space station, but in order to be able to study it, we need to be able to collect it and seal it in a vacuum. And then the thing we're using to collect it, it needs to be simple enough for astronauts to be able to use with pressurized gloves. And there needs to be a way for them to hold on to it without losing part of it.
Excellent.
I explained that to you. I know. Okay. For research, there are not any commercial products of this. Came up with the idea when I was having a conversation with my dad about the project, because we were really struggling about coming up with a solid idea that would really work. And then we added things to the initial idea to make it easier to use, and found the materials that it would be able to be made of, and that it would be able to work in space. The main idea is from the research we did was just to keep it simple and find the best way to seal it. So these were our initial ideas. The first one was kind of like a Swiffer idea, where it was basically just a Swiffer that we would put in an aluminum box. We hadn't quite figured out how to seal it yet. And then the other one is, we were originally thinking it was a sphere. I forgot to change that, but now it's kind of a cylinder. We went through, found all of the information for the different materials being used, what their melting points. I couldn't find the freezing points of any of them. I didn't think that was as big a deal. But basically the outside would be aluminum, and it would screw together. So outside is aluminum, and it's kind of like a cylinder thing. On one side there is nylon, on one side there's silicone, and then it would screw together to make to kind of make a static electricity. So screwing it together, that would create a vacuum. It would have to be closed in a vacuum. And then they would open it outside of the space station, and screwing that together, it would create it would create some static electricity, and they could just take one side of it, put it on the space station where they think the dust would be, and then they could just close it up again, and that would be their seal thing. So yeah. Criteria we need to meet is it needs to be small, needs to be simple, needs to be completely sealable, and needs to be able to reliably collect the dust.
Some of the constraints we ran into, if the material was not strong enough or if the seal was not good enough, it could implode due to the pressure change of going back onto the ISS, which is also part of number 2, the imperfect seal. If it doesn't seal correctly, not only will it be contaminated, it is also at risk of implode. And it needs to be able to use fast. So yeah.
Thank you.
It needs to be able to be used quickly because the gathering dust is not the main mission. So it needs to be something that can be done quickly and efficiently.
Within 5 minutes, yeah. For the Swiffer, which was the original idea, some pros to that were it was easy to make. It's been made before. It's simple design and it's easy to use. Cons is it could be kind of heavy. Corners, if they were too sharp, they could be an issue. It could end up just being bulky. And then sealing was also an issue. Originally, we were thinking a slide-on lid, but it was kind of unreliable. And then we were kind of thinking, Mr. Hill brought this up to me after the prototype for the sphere collector had already been made, but it could also be kind of like a test tube thing where it screws in and then comes out with the lid has the Swiffer on it. But yeah, none you do. Yes, you skipped half our slide. Sorry.
For the sphere collector, it needs to be simple. It's really simple. You just unscrew it and screw it back together. It's relatively light. It'll most likely be made out of aluminum, but that is a fairly light metal. It's easy to use, easy to make. It's also small in size. Our prototype is much smaller than it will be, but it's still going to be of a decently small size. And we ran into some issues figuring out how to seal it. At first, Devin had given us a few ideas with cold welding and quantum pinning, but after much research, you can't really test cold welding on Earth due to the oxygen in our atmosphere, and once it got back to Earth, it would be very difficult to undo that, considering it fuses the two metals together. So it wouldn't particularly be without contaminants because it would have to have metal flakes to be able to reopen it, because you'd most likely have to jackhammer it open. And the quantum pinning, after just much research, we realized it was not the correct thing for this project because it has to stay very cold in order to keep it in its quantum state, and it would just, after the 90 minutes of cold and night, it would just fail and fly apart.
Then it could implode if it's not sealed correctly. So our design of it, this is what we have right now. So basically we have the top lid, which is just one of the things that screws on. We have a connector that actually attaches to the top lid, that is able to spin around freely, so that we can connect the top lid to the bottom lid with like some string or a wire or something, so that we don't lose either side.
Okay. Hold on a second. I'm not quite sure I'm following. How are you gathering the cosmic dust with this stack up of materials? I'm not following.
It would be easier to show you with the prototype. Could I do that?
Yeah, let's do that.
Yeah, stop sharing and let's take a look.
Okay, so we have the prototype right here. This is like 3 times smaller than it needs to be because my 3D printer at home, we don't have that much filament.
That's perfect. Keep going.
So this is the connector that we would use. We would just connect it right here and like use like some string, like I was just saying, so that it could spin like itself. These parts that come out right here are just for better grip because like they're gloves.
For your hands. Okay, keep going.
It would screw apart, and once it's done, I'm gonna throw it. But no, it would screw apart and not like everything isn't attached, so I can take it apart. But like everything would be screwed in place for the like final design and everything. And then we would take, it would actually be this side. We would take this side and we have like little loops here so that we can loop like a handle or something so that they can just stick their hand through it and hold it like that. And then just put it on there, like on the space station. The way it actually makes the static electricity is one side has nylon and one side has silicone. We haven't been able to test what kinds of each thing would be able to work, but both of those materials would survive in space. And we were kind of thinking it would be like a balloon with hair or something like that, where it like picks up dust and stuff.
Okay, so let me see if I understand. So as you rotate these things to open them up, you're rubbing one against the other, and then you just put it up against the side of the space station. You grab a little bit of this dust, and then you put it back together and rotate it back. Is that it?
Yes. And we haven't figured out which side would be the one, like because we could put either material on either side. But I was thinking the side that didn't have this rotator bit would be the one that would go up and be put on there because that's the side that, like this side is the side that would have the handle. So then they can just like stick it up there and like not have an issue with that. It just depends on how the outside of the space station is charged, whether it's positive or negative.
Okay. All right. So with that idea in mind, choose your materials and then sprinkle some diatomaceous earth or something like that on the table, and after you rub it, just see what happens. Does that make sense?
Yeah. And if if it's
my thought is, if you put them together, I'm curious, you've attracted or repelled. Now when you put them together, are they going to are the dust particles going to stay in between? Because they might push each other as well.
I don't think the charge would be that strong as to physically repel them.
Well, what I mean is, so you've picked up dust on one or the other. Now, when you put them together, are you going to push the dust off, or is it going to stay between the two?
That is a good question. I am not entirely sure.
That's where testing helps.
Yeah.
We
I
haven't been
love
able
your
to fully
idea.
test it yet.
Hey,
I
let
love
me
the
make
idea. I
one
think it's really
suggestion
smart.
for you. When you described how as you unscrew this, you're going to be charging these. One of the discs will basically be positively charged, the other will be negative, right?
Yes.
Okay. You also said that on one of those two components, you're going to put a strap or a loop or something so that the astronaut can kind of slide their hand into it.
Yes.
You need to have something on the opposite one, or you need to have those two somehow bungeed together.
They are.
Because, go ahead.
So they're with the movable, like, kind of, here, let me just take that out so it doesn't fall out. The loop right here, this black piece, it connects to a small piece right here. And it would just be connected with like with some wire or some like a nylon string or something like that, so that it can connect together. And when it screws apart and screws together, this can move on its own.
Good
and
idea.
So we don't
Yeah.
have it.
Yeah. Okay. So you thought that through. That perfect. Very good. So how in the prototype that you have, how much surface area will these discs have? How much dust could you potentially be trying to pick up?
Well, it depends on the amount of dust that would be in the area. I'm not sure how, like, because you're asking how much would be on these discs.
I'm just basically interested in how much surface area are you going to be able to make contact with?
Okay.
You know, as you start to put this on the surface of the station, right? Is it designed so that you could kind of touch it and do it again and again, or is it just a one-time contact?
Well, I'm not sure how strong the static electricity charge would be to like if it could be touched multiple times. I was originally thinking just one, like that was our original thought.
Okay.
But yeah, as for the surface area, we hadn't come up with the final like size of it, but we were thinking it would be like about that big or something, not like the like this big in general, like the whole thing. And then disc is a little bit smaller than that.
Sure.
But
So I
like,
guess what you're telling me is that you have one prototype here, but you may actually increase the size of the whole thing. Okay, very good.
yeah, for the final size of everything, it would be bigger. And for the prototype, I have everything, like we have everything so they can just fall out. And so we can take it apart completely. For the final design, it would be made so that it is like, because in this, there is one part that I didn't get to is how, like, because we thought about how when it screws, the like if we had it just connected to this side, then like that would just be at one point, and then at a certain point in the screw, it would stop like doing that. How we have it is we have it's shown on the slide, but I can show you if I can get it out. But we have a little like really thin disc that I don't know if I can get it.
Yeah,
So that,
I see it.
so that it just pushes it up with the 3D printing. It's so thin that it doesn't want to stay up. But like if that was made out of like some thin aluminum or something, then that would be able to work the same way. Originally, we were thinking screws, but that would be kind of unreliable because they might move or shift or be difficult to use. But that would like compress as they screw it down, and then decompress as it gets unscrewed, so that the faces can follow each other, like so that this part would like go up as it's so that it stays on this part until it's done being screwed.
Okay. So one thought I have for you is that when you do your testing with your two materials, right, I bet you don't want to actually touch the surface because then I think you'll discharge the static that you've got on each of your things. So it's kind of like getting down close to the surface with it, attracting it and getting it, and then putting them together. And I'm thinking that you can probably kind of, it's not a wipe because you're not touching, but kind of hover over a long area to be able to gather a larger amount. So I think there's an interesting idea here. I would love to see how this works out. Now, what two materials were you thinking of? You're like a silicone and a what?
And nylon.
And nylon.
Yeah. So like
I think that's a
nylon
smart idea. Yeah, I think that's a great idea. Give a couple of different things a try and see how it works. You might be looking at like a wool and a plastic or like an acrylic or something like that. Those are all good ideas to be able to generate some static electricity. Good idea.
And we generate a lot of static electricity here in Montana without even trying.
And that's a problem here. I can't do hardly any static electricity projects here because it's so moist. We can't hardly generate it.
Yeah. So, but I liked your suggestion, Glenn. Maybe they don't even have to touch, and you should test this out. Maybe if you get enough static electricity, you don't have to even touch the outside of the space station. You can just run it real close over a whole area. That would increase your amount of cosmic dust you get.
Yeah.
So
I think
really
that
nice.
Your material you could just have recessed inside so that physically they could actually like touch the rim of the container to the surface. It would be kind of hard if you think about it, to control it and hold this at like, I don't know what, an eighth of an inch or something right above it. So all you do is just kind of recess the material inside, and you could play around to figure out what the optimal distance is going to be.
Wow, that is good too. Yeah, thank you. Yeah, very interesting. Very interesting. Good job. Awesome. Do you have any questions?
I don't see you.
What would we test our project on to see if it can actually pick up and hold a charge in this thing?
Right. So, something. So, and I don't think you have to build your whole assembly first. I think you should get your materials and find out what materials you need, and then figure out how you're going to attach them inside. And then the kind of powder or dust that you put on the table. So diatomaceous earth is something you might be able to get at the hardware store. It's a very fine powder. They're actually they're dead microbial animals that were in the ocean a long time ago, so you probably won't be able to see the individual particles, which is why I'm suggesting it. But also, it's made out of like they're like similar to like a quartz kind of thing, and so I think it'll have some similarities to what we would be trying to pick up off the space station. Okay.
All right.
Excellent job, team. Good job.
Awesome. Thank you so much. You guys have a good afternoon. There's another dust collecting team.
Excellent.
Yep.
Thank you.
Thank you. And this team is freshmen at Laurel High School, which I'm really pleased that we have some freshmen, and hopefully they will participate for all 4 years in high school.
Excellent.
Because the class is you can get credit every year I forget what it's called. We see your PowerPoint. Introduce yourselves.
So, I'm Kaya Rosenberg. I'm Claire Devaney.
I'm Preston Price.
Do you want to talk about we're doing the cosmic dust collector. Yep.
So are you ready?
Yeah.
We're ready.
We're getting our PowerPoint.
Okay. We see a PowerPoint up that says research.
I just want to make sure they can see it too.
Yeah. Thank you so much, Devin. So Devin is the tech person for the school and was a Laurel student. I'm not sure if he was ever in HUNCH. Were you in HUNCH, Devin?
I was not in HUNCH.
But he runs the 3D printers and he's helping this class tremendously with their all learning 3D printing.
Terrific.
Okay. Thank you.
Okay. So most of our project is made of silicone and stuff. Anyway, currently NASA needs to find a way to collect pure uncontaminated space dust to study and examine. The problem they are facing is they can't find an efficient way to collect the cosmic dust and contain it from earthly contaminants. So there's our problem. So mostly it's just kind of like thoughts that we've had, and then we are not very good at 3D printing and like smart stuff like that. So we mostly relied on like household stuff. So there are commercial products that we definitely used. We got most of our information from the slides and stuff on the HUNCH website, and yeah, and then our project needs to be easy to use in a spacesuit with the big bulky gloves and stuff. It needs to protect the dust from contamination. It needs to be small and simple, and the scraper needs to be able to catch the space dust that has a mass of very, very tiny. And then, so we were thinking about something collapsible made of silicone, so it can vacuum seal in a way, but also be small and simple. And then the lid can be compatible with that. So there's that. We had a lot of ideas when we started doing it, like different ways to do the lid and attach it. Because the first way we started doing it, we thought we were gonna attach it to the space station itself, but then we later learned that they wanted to like take it out and quickly collect dust. Yeah, so we were thinking of scraping the dust off the side with the lid as the scraper kind of. And then there would be a metal plate in the bottom of the bowl, and that would be charged with static electricity, and it would act as kind of like a magnet to catch the dust. Yeah. we kind of already said this stuff, mostly just not very complex, and needs to be temperature adaptable for the hot temperatures outside space stations.
And cold?
Yeah, and cold temperatures. The container will be silicone, and when it's pressurized, it will be able to collapse and sink. And then it will be attached to the astronaut, so they don't really have to worry about it like floating away or anything. And then the cons are the scraper might be difficult to use. And then we thought about magnets and stuff, but that would take a lot longer to collect the dust. And then there might be complex parts that we have to worry about. So we aren't very good at this, but so it'll be like a household Tupperware that can collapse and then have the lid have a handle on it, so you can like scrape it off like this. And then the scraper itself will be metal with nylon on it, so the fibers can catch the dust. And then it will be able to like retract out of the lid with a hinge, and so you can just scrape it right off.
Do you have a picture of your scraper? What kind of scraper do you mean? Like a spatula? But then you said with nylon. What do you mean?
Yeah, and then it'll just have like a layer of nylon on the outside, so the cloth can catch the fibers off of it instead of just being.
So it's a nylon cloth, not a nylon solid plastic.
Yeah, no.
Well, it's like it's like a metal plate with nylon over it.
Yeah,
scrape it.
Okay. And how does it? And so you'd take it out of this container and then scrape it on the side and then put it back into the container?
Yeah, so we were thinking that the dust would be attracted by the static electric magnet type thing on the bottom inside of the bowl. And so it can just be there, and then you can get as much as you want off of the side.
Okay. And so where there's something inside? You said static electric magnet. Which one do you mean? How did you want to put that in there?
So it would be on the inside bottom of the bowl. Like if you were to do a bird's eye view, it would just be in the bottom. And then it would be a metal plate charged with static electricity to sort of work as a magnet to attract the dust.
Okay. Based silicone. Okay. And so so both parts are, so it's kind of like those like a rubbery, like a bowl, a silicon rubber bowl with a silicon rubber cap. Is that correct?
Yeah, we have it.
Oh, you got it?
Yeah.
Oh, well, I want to see it. That sounds good.
Oh.
Well,
yeah, you just hold it up. Yeah.
Yeah. So we got a silicone bowl, and we put Velcro on the bottom to spacer right here. And we haven't gotten our metal yet, so we used a piece of paper to like act in place of it for right now, and so it'll be in the bottom. And then there's the lid.
Okay.
It has a handle.
And now
on
when
it.
you push down on it, how's that work?
And then it'll collapse down. So when it goes inside from not having air in it, so instead of breaking, when it collapses, it'll just like shrink down.
Okay. All right. That's interesting. So so here you want to put the spatula that you're going to open it up, pull out the spatula thing, scrape, and then put it inside and then just close it back up, right?
We were thinking that we didn't have time to actually make one, but like this paper would be
Like it'll attach with like a hinge and like
and then
out.
flip out. So this will be the thing, and then it will. You'll be able to like go like that, and then the scraper will be here, and then
So the scraper. So when you pull it open, you're going to do the scraping with the one piece, and then what you do is you put it back together. Is that right?
Yeah.
That's actually pretty interesting. And you know, if you had two handles, so you put a handle on the bottom of your cup as well. So you pull it apart. Both of them are attached to your hands. Scrape, scrape, scrape. Put it back together, and you're all done. Is that right?
Yeah. Except we just have stuff because we heard that the astronauts have like Velcro on their sleeves, so that we put Velcro on the bottom and like stick to it, so then they can just like off and then go like that.
Okay, that's interesting. I like that idea. That's kind of cool.
I think their bell rang.
Oh,
yeah.
Okay. Dave, did you have any comments for him? Oh, you're still muted, Dave.
Yeah, sorry. No, you kind of covered it. I don't. My comments would just be redundant at this point.
Awesome. Well, I like how you're using commercial off-the-shelf products to design. You should learn 3D printing as much as you possibly can while you got those other people there doing that for you. Do you have any questions for us? Okay, so I like your idea. Test it. Use the same material that Glenn suggested and test it, because it's a very unique idea also. And I'll try to come and visit with you. But take videos if you do test anything. Okay. All right. Great job. Thank you. So we didn't get to see their other teams, but you know what? I'll go and do their PDRs in person. So I'll communicate with they have ejecting robot and a camper, but I'll just go and see their PDRs in person because their teacher isn't there. So, but Devin is there. So that was Devin. Thank you so much, and I'll communicate. Yeah, that was a really good presentation. We could hear it, and thank you for helping them with the 3D printing and all, because they don't have that in their classroom. Devin has it at the library that has a room full of 3D printers. So we got a little break until 15 minutes when Jackson Hole is joining us.
Oh, we got 15 minutes right now?
Yep, till Jackson Hole joins. They're supposed to join at 1:30. So
I'll come back on in a few minutes then.
Yeah, thank you. Okay, I'm going to
leave this open or just?
I'm going to leave it open. I'm just going to pause the recording.
Okay.
Awesome. All right. Well, I'm recording it, so if Glenn joins us, that would be great. But we do have Dave, who does a great job.
And you can see your screen, yeah?
Yeah, we see your PowerPoint. Looks awesome.
All right. Yeah, let's get after it.
All right. So I'm Owen Schultes, that's Boomer, and we're missing Blake. We're from Jacksonville High School in Wyoming. Mr. Anderson is our teacher, and we are working on like the additive manufacturing of a lunar tent stake project.
Okay, so this is a look at our initial research page. Where should we start?
Yeah. I mean, we kind of spent a good deal of time researching kind of like common tent or other stakes that could help like drive our project. These are a bunch of like solutions that we found, like trampoline wind stakes, drywall anchors, like drill and tent stakes. We got like this one's like flat headed. Then there's like mechanically barbed arrow. something like that. So we're kind of like looking at like what we might use to help our project, especially if like this drill kit, we could like figure out how to use that as like our thing.
Yeah, this is just like an array of all of our ideas. So we kind of labeled them with like will use, maybe not use, but it's good to like have all these ideas so then we can like dumb them down once we get closer to like testing and stuff.
You bet. And somebody mentioned that drywall anchors before when team was discussing this. And that's the first picture I've seen of it. That's awesome.
Yeah, no, these are super interesting. Like we looked at like two different ones. Like this one kind of splits the ends here, and the other one it kind of like expands into the wall. Which those two are definitely both like interesting, at least.
Yeah, yeah. And Glenn joined us. Hi, Glenn. We just started.
Oh, sorry. Here comes.
Oh, here he comes.
Here comes Blake.
Oh,
yeah.
Sorry about that. I had some issues with my teacher letting me out.
Yeah, yeah. Okay, good. Well, now we're all here. Keep going.
Sorry about that.
All right. And then brainstorming. So we kind of like looked at the brainstorming process. We kind of looked at a bunch of different solutions, sketched a bunch out. These three are kind of like a twisted spiral stake, which kind of like twist into the ground almost, but it also be drilled. The other one's like kind of like a hollow spiral stake. So that one's more like kind of like a spring shape almost.
Yeah, it's a very minimalistic, minimal stake. We doesn't have a lot of support material. So we're kind of like figuring out maybe if that's going to be the best solution because Blake had another design here.
Yeah, it was kind of just one if that middle one isn't like supportive enough. That one does use a little bit more material, but it might be kind of less fragile when putting it in the ground. We still need to do like a little bit more of the testing to see that, but it's obviously gonna be a little bit more supportive just because of that stick in the middle. Kind of how we came up with these is we made I think 9 to 10 designs, kind of different brainstorming ideas. Then we went through a decision matrix, kind of rating different parts of them, like the amount of material, how sturdy they are, how drillable, kneeling, kind of all these factors. And then these were our top 3 designs that kind of won out of the matrix. So that's kind of how we came up with these actual designs.
Yeah. And then CADing. So far, we've CADed a couple different models. This one here on the left is the one that we've actually made a prototype of. Yeah. So this thing is 6 inches long. It's got like 12 revolutions going around it. And this was kind of going off that 3rd design on the last page. It's got a sharp tip on the bottom and then for attachment. And we just didn't really know what we wanted to do with the drilling mechanism or all that yet. So we kind of just left that.
What direction do you plan to print that one?
We printed it flat, kind of on the bed like this.
Okay. So, how much? What kind of support material do you get out of that?
It was. I mean, we collected it all so we could like measure it and all that. It was a little bit, definitely a lot, but like I feel like we also could get that down. We have some like ideas on how to print it better as well.
Okay.
And then our other 2 CADed models, we have our hollow spiral, which is the one we briefly discussed. Then we have one that might work, might not. We're not too sure about it. It's the barbed one. We don't know how well the barbs will go in actually drilling it into the ground, but we feel like if the barbs can collapse in and expand out when it's in the ground, it will make it like much more sturdy while in there. But that's kind of we still need to do some testing on that.
Well, so if you have barbs that move, doesn't that also imply that it's multiple components?
Yes, that's why it's a little bit more complicated because we are afraid they might snap off, but if they're made out of aluminum, they might bend or like bend into the ground because they might like twist with the stake. So that could be beneficial. That's kind of why we're saying some more testing needs to be just to see how the actual barbs sticking out react when going into the ground.
Sure. And just to be clear, I'm not against having multiple parts, but make sure that it's something simple to assemble for the crew.
We're still deciding whether it should be part of it or you assemble it on. We're going to try both methods. That's something we'll decide in testing.
Yeah, we're planning on making quite a bit more designs, I think. So we're kind of like at the surface right now. This is the actual prototype we have. We have it right here as well. 6 inches long. I don't know if that's, you can see it there.
Now, does that loop, are you worried about that loop being something that we could trip on?
Yeah, so that's what I was going to bring up a question later. We're trying to figure out maybe like it's collapsible in some way because Mr. Anderson as well like talked about the tripping hazard. So I mean, we have some ideas, but I mean also your guys' input would be very beneficial as well.
We're kind of thinking this loop, but like think of a little hinge here maybe. Again, that would require 2 parts, which we don't really want to do. Because assembly and everything on the moon is quite difficult, but we're thinking maybe put it in like this, you attach everything and then it bends down so it's flat like on the ground while still holding it down. That's kind of an idea we have so far that we still need to put into practice. We're still kind of working on that.
Yeah, this is very rough. We'll see what we do with the loop. Like, we're not sure if that'll make it. We kind of just wanted to have something physical.
So far we've hand twisted this into the Quikrete. It stuck pretty well, but we couldn't get it in all the way, which is kind of a good sign because with a drill you'll be able to, but with your physical hand it won't, which just means it'll be kind of more sturdy when it's held in there.
Good, good. Okay, keep going. You got another one there?
This is the only prototype we have right now.
Oh, okay. I thought maybe you'd printed the other ones yet. Okay.
They are currently like in process of printing.
Yeah.
Very good.
So then kind of like what we're doing for the future, we have a data table that we're going to try and fill out. This is kind of what we're mostly looking at, like what printing material, the infill, the mass of that stake. So like how much material it needs, the support material mass, and like forces measuring that, and then like just other stuff.
Plus the test you've given us to like test, angled forces and everything. That's obviously going to be something we factor into this.
Very good.
So, yeah.
Now, the other thing you might want to consider having on there is just a description of what the mass would be if it was aluminum. It's not.
Yeah, that makes sense.
It's not a critical thing, but it could give some help if there's
we can definitely do that because right now we're just comparing the masses of each. But then we can translate that to aluminum once we find like our final stake and kind of everything like that. We'll kind of translate every aspect of it being, the 3D printable material to the aluminum material to kind of see how that works, if that makes sense.
Sounds good. Now tell me about your test bed here. I see you've got how did you mix up your concrete mix?
Well, we kind of we poured it in and then spent a little time like shaking it around. Like we didn't ice.
Kind of how people like churn butter. We kind of did that, I think is the best way to describe it.
Sure. Then make sure you tap the side, right?
Yeah.
All the vibrations that you get are going to make it kind of compact down a little bit. And I think that's going to be a lot more realistic for the lunar soil as well. Okay.
Definitely.
Yeah.
We compacted it down, it's kind of where we want it right now, but we might mix it up some more just to kind of see different effects of when you're testing on different terrain, I guess, if that makes sense.
Sure. Now, so is this a mixture of like mortar and then you put some gravel in it, or is this just straight post if you're like putting in signposts or whatever?
We went to the hardware store and just bought like a bag of Quikrete.
Okay.
Some
I think that has a lot more gravel in it than what's going to be correct for the moon. I think that if you take out some of that gravel, it'll probably go in a lot better and it'll be more realistic for what we're trying to do. Okay.
We might get another bucket and a different kind of Quikrete, and we can just compare the two. No such thing as too many testing.
Yeah, that was fun. We had some questions. That was kind of one of them. Like, should we be trying a different sort of something or whatever? Yeah,
and I think I described it a little bit in there. I think it was a mixture of like mortar for like what you'd put between bricks, and then you throw some gravel in there along with it, right? I'll have to look at that because I can't remember it. But Dave and I were talking about it a little bit earlier, and I thought, gosh, I need to look at that again to make sure that we get it right.
Yeah. So yeah, that's kind of like the end of our presentation, I guess. We had a bunch of questions that we wrote down, at least.
So,
I guess,
guys, we can answer the questions, but if you would, do you have your prototype there? Can you stop sharing and let us take a little closer look at it?
Of course. There we go. All right.
Sure. So yeah, this is this guy. You can see it full screen.
And what did you print that out of?
This is PLA.
PLA. And you said in your chart, it said you have a 20% infill.
Yeah.
So how thick do you think the walls of that main shaft are?
I mean, like it feels sturdy. Like I wouldn't say they're necessarily thin. I couldn't tell you though, I guess.
Okay. I think that I like that narrower shaft. I mean, it makes a lot of sense to me, but the question is, will it be strong enough, especially when you start augering this down under power, is this thing going to kind of bend and twist on you?
Right. Mm-hmm. And I think that the top piece that you have, I think that's much larger of a ring than what you'd probably need. You can shrink that down a little bit. But also coming up with something so that your drill can attach to it and be able to drill it in is going to be really important.
Yeah, there are these drill bits that instead of like connecting, they kind of go over, kind of think of it like this, and then they twist it like a circular piece that you can just put on a drill or an impact driver. Okay. I forgot which one, but it'll basically kind of collapse around this, twist it in, and then you can just take it off, and it'll leave that part around on the top.
Okay, and I'm all right with how you want to do that. It's a matter of you're working to make sure that you're not going to be tripping on it, but it's also easy for you to get a rope through there, and so there's all kinds of give and take on it.
I was also wondering, this is a question. It has to do with our project, but it's like kind of outside. Should we make a 3D printable drill attachment that's specifically designed for our stakes that we can 3D print on the boot to kind of like save storage space in the actual shuttle?
Sure. So if you have a specific way that you want to attach to it, then whatever. I don't care what kind of drill you have, but you need to have something so that we can see how you plan to drill it into the ground. Okay.
Yes. All right.
Excellent. Good. Thank you. Now you had a couple more questions there. You want us to answer those?
I mean, this one's kind of like, should we try to figure out like force measurements for if we had a longer screw? Because this is 6 inches, but you were looking at 12. Like, should we try to like maybe calculate that or find actual like aluminum?
Or no. And the reason is because right now we're trying to test everybody's in the same fashion. And so the only thing that matters is how much force does it take to take it up, straight up, and then how much force does it take to remove it when it's a guy wire. And so we want to have a consistent way of measuring everybody's, and then we can compare and say, well, the real length is probably going to be 18 inches long or something like that. But having several different styles that we can all compare in the same fashion is important for us to understand what we're really trying to get in the end. Is that okay?
Yeah.
Okay. Excellent job, guys. I like what you're doing.
And one last question. Is there a preference between Phillips head and flathead drill bits when going in?
I wouldn't use either. I personally, what I would do is get a socket.
Yeah, that's what we're thinking of. But like, if we were to build like a socket head, then you could like let's just say use a Phillips head to use that kind of connects together. Is there a preference between those two?
I don't think so. I mean,
perfect. All right.
I like a flathead myself, or excuse me, I like a Phillips head myself, but there's just because when you're using a drill, it seems like it always walks off the side. So,
okay.
But how you do what works for you guys so that you're showing us your best foot forward. Okay.
Perfect. All righty.
Keep it up, guys. I like what you're doing.
Perfect. Thank you. All right.
Yeah, good job. And you can always ask questions anytime. Just send them to me. All right. Well,
perfect. Thank you.
Thank
you guys
you.
have to say.
Yeah, good. Great job. Thank you so much.